up on there. We passed it off first game. I was probably
I might be in the class.
Have you played Thunder yet? You did. No, you respawned.
All right. Let's go ahead and we're going to open up to page 418. We're going to take a look at two more kind of graphical examples of this second fundamental theorem of calculus. Can we perhaps summarize that theorem a little bit? For instance, when should we realize that we have to use the second fundamental theorem of calculus? What is it used to do, or what is it used to find? Yeah?
You find the derivative of an integral.
The derivative of an integral. Okay, so keeping that in mind, we got to ask ourselves, whenever we're finding the derivative, if it ever involves finding the derivative of an integral, we're going to utilize that theorem. So on page 418, it says, let capital F be defined as this integral from 3 to x of little f, and the graph of little f is shown. So graph of little f. I guess what the first thing we're going to do is to try to figure out a small table of values for this capital F of x function. So we're going to take these various x values and plug them into this function. So if I'm plugging in 2 for x, notice how that's going to involve plugging in 2 for x as the upper bound. So if I initially write that out, this is kind of what we have. So essentially, to figure out this f of 2 value, we have to look for the area under the little f graph from 3 to 2. So we're looking at this little strip. Do we notice anything interesting about that integral?
Yeah.
What about it?
The bottom's bigger than the top.
Bottom's bigger than top. So if we got to flip the bounds,
Make it negative.
we're going to make it negative. Okay, so whatever area value we find here, we're just going to have to negate it, make it the opposite. So let's see. This geometric shape is a trapezoid. We would need negative 1/2. The height would be 1, and the parallel bases are 4 and 6. So we know that this area is negative because it's under the x-axis, but if we then have to negate it because we flipped the bounds, realize that this area is now going to change to a positive value. So it looks like we'll have half of 10, which would be 5. So there's our output value for capital F. All right, we're just going to repeat the process for these other x values. So to figure out this point, we're going to plug in 3 for that upper bound. We need the area under the little f graph from 3 to 3. So we're starting our area calculation at 3 and we're ending it at 3. Zero. It's going to be 0, right? You don't span a period of time. You don't have an actual interval to use. You're beginning and ending at the same spot, so our area would be 0. All right, for the next one, we'll go from 3 to 5. So geometrically, that would be a triangle. The entire triangle is underneath the x-axis, so we'll need negative. See, our base is 2, and our height is 6. So it looks like we'll get negative 6. Let's see, for the next one, we'll go from 3 to 6. So we basically need the same area as we had before, so the same negative 6 value. We now just have to compensate for this extra piece that's above the x-axis. So I gotta take this -6 plus whatever area this is. So 1/2, the base of the triangle is 1 and the height is 3. So that would be 1.5. So -6 plus 1.5 would be -4.5. Let's see, our last one will go from 3 to 9. All right, so we're going to add on, maybe I'll use a different color. Okay, so we're going to take the same -4.5 that we had, so that's all this black area, and we have to add on the rest of this red shape. So let's see, initially we have this trapezoid, and then the rest of it is a rectangle, so we can maybe break it up that way. The base of this trapezoid is 1, the parallel sides are 3 and 6. And then we'll add the area from the rectangle, which is 2 by 6. So we need -4.5. A half of 9 is a +4.5, and then we have to add 12. So looks like overall we'll get 12. You doing okay? It's kind of an accumulation. You just keep adding the area depending on the bounds that you have. Let's see. On which intervals is little f positive? Can we use the graph to help us out? Yeah, can we give an interval? Where is this graph positive? 5 to 10, because it's above the x-axis. F of t is above the x-axis. Looks good. So on the flip side, for number 3, where is it negative? We could probably say 0 to 5, because f of t is below the x-axis. All right. 4 is going to switch it up a bit. On which intervals is capital F increasing? What do we have to analyze to help us determine increasing and decreasing intervals? What tells us if a function is going up or going down? Slope, aka derivative. Okay, so can we take the derivative of capital F? Notice how at the top we have an equation. So to take the derivative, that's going to involve taking the derivative of an integral, aka we're going to have to use that second fundamental theorem of calculus. So we're going to take the upper bound of x and plug it in. Then what? Derivative of x, which would be 1, okay, minus plugging in the bottom bound of 3 times the derivative of 3, which would be 0. So after, there we go. And f of x times 1 is just f of x. All right, so take a look at what this statement is telling us. The derivative of this capital F function is exactly the same as the little f function. So if this, all right, if this is the graph of little f, what also does this graph represent? And f prime, because they're equal, right, based off of this statement. So we'll say and the derivative of capital F. So maybe we can now use this graph to help us figure out where capital F is increasing. If this is the graph of capital F prime, what should we be analyzing on this graph to see if capital F is increasing? What does a derivative have to be for capital F to be increasing?
Positive.
Positive. Okay, so where's this graph positive?
5, 10.
5, 10, just like we said in number 2. 5 to 10, because now our reasoning is going to be a little bit different. Because now we're with the understanding that this is the graph of the first derivative. So we'll say because f prime of x is positive, okay, or above the x-axis, whatever phrasing you want to use. Very similarly, if this is the graph of the first derivative, we need it to be negative for decreasing for that original function. So we'll say 0 to 5 because the first derivative is negative. Okay, so we just made a pretty big connection here. Not only is this the graph of little f, but it also represents the graph of the derivative of capital F. So we can use that to our advantage as well. If this is the first derivative graph of capital F, can we find some concave up and concave down intervals? What should a first derivative graph be doing, or what characteristics should it have in order for that original function to have some type of concavity? Can we think of about what property or characteristic we should be
Negative to positive.
Okay, so if it goes from negative to positive, that would be a minimum.
Yeah, I meant, yeah, never mind.
Okay, that's fine. Okay, so this would be a minimum on capital F.
Is it decreasing, increasing?
Yeah.
That's what I meant to say.
Well, good catch. Okay, so if we're concave up, let's think about it. Because the derivative is what? If we want a concave up interval, the first derivative should be increasing.
Yes.
Okay, so based off that justification, this first derivative graph is increasing from 3 to 7. Or is that 6? Is it 7? Okay, 3 to 7. Sounds good. All right, so then on the flip side, if we want to concave down, the first derivative is decreasing, so that would be from 0 to 3. What's happening on this interval from 7 to 11? Or 10, rather, where it ends? No concavity, so there's no curvature. Can we think about what type of, or what the graph might look like on this interval if there's no curvature?
It's a leveling point.
It's a level, it could be, well, it can't be level because the derivative isn't 0.
Really true.
It's so if this horizontal line was down here, it would be level. Notice how it's a line. The slope is 6, right? The first derivative value is 6, but there's no concavity, so you have a line with a slope of 6, okay, on the original graph somewhere. Good job. All right, let's go ahead and try another one. 419. Picture to the right is the graph of little f, 2 semicircles and a line segment. Interval 0 to 17. G of x is defined as the area under the f graph from 0 to x. All right, let's try the first one. G of 8. What do we feel like doing? And crying is not an option. Yep, plug in 8 for the integral, or that bound. Okay, so this 8 is an x value. We'll plug it in for that upper bound. So we technically got to figure out the area under this F graph from 0 to 8. So we'll stop right there. So visually, it looks like we need a half of a circle and then a quarter of a circle. So a half a circle will be 1/2 pi. Our radius is 2. But then we have to subtract this quarter circle because it's underneath the x-axis. So that would be a 1/4 pi, and our radius is 4. So a half of pi times 4 would be 2 pi. And then a quarter of pi times 16 would be 4 pi. So overall negative 2 pi. All right, so we're down with the first value. Let's try the second one. We got to figure out the derivative of g at 8. We'll tackle the derivative first. So if I want to take the derivative of g, aka the left side of this equation, I then have to take the derivative of the right side, and notice how that involves taking the derivative of an integral. So we're going to use that second fundamental theorem. We're going to plug in the top bound, which would be f of x, okay, times 1, minus plugging in the bottom bound of 0, times the derivative of 0, which would just be 0. So it looks like we're just left with f of x. Okay, some of you might be able to go straight there, okay, simplifying it in your head as you go through the theorem. That's completely okay. If you got to write everything out, that's fine too. So with this first derivative equation, let's now go ahead and plug in 8. So if I plug in 8 for this x, I then have to plug in 8 into the x for the f function. Do we know what f of 8 is? Negative 4. Yep, this was the graph of f. All right, so we got negative 4. Okay. All right, let's try our last value. So now we want to figure out the second derivative of g and then plug in 8. So here's our first derivative equation. I kind of boxed it in. We got to take the derivative of this. So that means g is going to gain a prime mark, but then so is f. Take the derivative of both sides. So now let's plug in 8. So the second derivative of g at 8 is the same as the first derivative of f at 8. Can we figure that out based off the graph of f? What is the slope at that point? 0. If you draw a tangent line, it would be flat. There we go. Looks good. We hanging in there? Yeah? Okay. So let's go ahead and make this connection. This first derivative that we took might be something noteworthy. Notice how we just stated that the little f function is exactly the same as the first derivative of g. So not only is this the graph of f, but now you can add in, it's also the graph of g prime, okay, the derivative of g. So we might have to use that actually for the other questions. So for instance, on which intervals is the graph of g concave down? So now that we officially know this is the graph of the derivative of g, we can use that to our advantage. So what should we analyze about this derivative graph to see when the original is concave down? Can we think of our justification before we actually figure out the intervals? Decreasing. All right, so our intervals where we're decreasing 2 to 8. Okay. Should we be leery of any point between 2 and 8? Leery of where? 4. Why 4? It's a vertical tangent, okay? If you think about, remember these are semicircles, so the left and rightmost sides are going to be completely vertical. So where this left or this right side meets the left side of the semicircles, you do have a vertical connection there. So we have to be careful. I know it seems like you're decreasing the whole time, but technically the derivative of this graph, okay, the slope, does not exist at this point. So that would mean like G double prime does not exist. And if the second derivative doesn't exist, there's no way your original function could be concave down. So we have to be a little leery of those locations. Okay, so I know it seems like it's decreasing, but we have to be careful of that spot. So let's try the next one. On which intervals is the original graph increasing? Can we think of our justification? What should the first derivative be doing? Or a characteristic it should have? Is positive. Okay, so this graph is positive from 0 to 4 and 12 to 17. All right. Find all values from 0 to 17 where G has a minimum. Can we think of our justification? What should the first derivative do in order to create a minimum? Equals 0. There we go. And changes negative to positive. So can we find a spot, maybe there's more than one, where this happens? Where do we equal 0 and change negative to positive? Is there any spot that fits that description? Where are you looking?
I'm looking at 4. Wait, no, I'm not. I'm looking at 12.
12. Okay, so this is where it's 0. This is where it changes positive to negative, and you guys are leery about the fact that it's a sharp point, right? So if it's a sharp point, that means the derivative does not exist. So if this is the graph of G prime, the derivative of this graph would not exist. So that would be another instance where G double prime doesn't exist, okay? But this point does satisfy this criteria because the first derivative is 0 and changes negative to positive. So x would be 12. All right, last one. What are the x-coordinates of each point of inflection for the original graph? Can we think about our justification? What characteristics should the first derivative have in order to classify a point of inflection?
Okay, if you said this right, you know it's right. So I'm just saying.
Has a max or min. Okay, so can we find those spots? Where does this first derivative graph have a max or a min? 2, 2, and 8. Looks good. All right. I think we're ready to try an actual AP question. So if you can do me a favor, try to find like a scratch piece of paper or the back or an empty page on the back of a homework section or a note section.